Welcome to Contemporary Math. Today we're going to start Chapter 2, which is Basic Set Concepts. And sets form the basis of everything, or most things, we're going to be doing in this course. This first part is heavy on definitions and notation. I know it's going to be tedious, but there's not really a good way to avoid that. Okay, so let's just jump in and get some definitions going. First of all, what is a set? A set is a collection of objects whose contents can be clearly determined. Now we have what we call a well-defined set, which I'm down here, and it just means that your average thinking person can decide whether or not something belongs to a set. There are no opinions involved, okay? So an element or a member of a set are the things that are contained inside the set, okay? We generally use capital letters to name sets. And with one exception, sets are written within braces, which are these little squiggly bracket things. If you need to look for these when you're doing your homework, you can find them on your keyboard. And also, I believe they show up in your toolbar, so you can just click on that and get those done. Okay, so now we're going to be talking about the exception to this. What we call the empty set or the null set, depending on which textbook you use. I think this book calls it the empty set. I learned it as the null set, and I will probably slip up and call it the wrong thing. So I'm just giving you both names. This is the set that contains nothing. It doesn't contain zero. It contains nothing. Okay? There are two ways to designate the empty set, and one is just you're going to see the braces with nothing in the middle. You are going to see this a bit on the homework, but we don't generally write an answer this way. Most of the time, you're going to see this symbol, which is the symbol for the empty set. And when you need it in the homework or on tests or anything, this will pop up in the little toolbar at the bottom, and you can just click on it. Now we need to talk about natural numbers. Natural numbers are just the counting numbers. They start at 1 and they go up by 1 every time. 1, 2, 3, 4, so on. And they go on and on forever. The symbol we use for that is either a bold N, a bold capital N, or you might see it like this. And this is called, this font is called Blackboard Bold. And it was developed because in print, everyone was using bold, but when teachers needed to write it on the board, we can't write in bold on the board. So this notation popped up, okay? But they mean the same thing. They mean all the natural numbers. Okay, so those definitions so far. Now we're going to talk about the 3 different ways to designate a set. And in the homework and everything, you will be asked to give some of these. The first way is a word description. And this is just a set described in general English. So the set of all natural numbers less than or equal to 6. This is well defined because if I gave you a number, you could determine whether or not it was a natural number, and then you could determine whether or not it's less than or equal to 6. There would be no opinions, no arguments. It is what it is. Okay, so that's word description. Then we have the roster method, which lists all the elements of the set, and they're listed between braces. Okay, so right here, the set of all natural numbers less than or equal to 6. Another way of writing that would be W equal to, between braces, 1, 2, 3, 4, 5, 6. They're talking about exactly the same set here. Okay, and I just realized I forgot to say up here, I said with one exception, sets are written within braces. The empty set is the one that is not. Okay, now coming back. So we had the word description, we had the roster method, now we have set builder notation. This notation can be a little confusing, although it's not really difficult once you know how to read it. The example below is read. W is the set of all, which is how you read the braces, the set of all elements X, such that is that line right there. X is a natural number less than or equal to 6. So this one tells you what it is in English. This one lists everything. And this is sort of a combination between the two. This one tells you how to, it just sort of gives you the rules to keep building what you need to build. Okay? They all have advantages and disadvantages. This is great when your set isn't too big and when it has some sort of pattern that you can establish, but a lot of times listing everything is just going to be impossible. Okay? The English description, well, you know from working word problems that going from English to math can be a little tricky. So most of the time you're going to be seeing set builder or roster. Okay, so now some more notation. We're going to be often asked whether or not something is an element of a set. And remember that an element is a member of the set, something that's inside of it. So a member or an element of this set would be 3, because 3 is contained inside of it. And 7 is not in there, so 7 is not an element of the set. Now this notation we use, it looks like a little curvy E, and here is a little curvy E with a line through it. These will pop up in your toolbar when you're doing your homework. This one is read is an element of, and this is read is not an element of. So we had the line through it just like we do in so many different things, meaning not. Okay, so if we use the W that we were talking about here, 3 is an element of W, but 9 is not an element of W. Okay, so let's keep going here. More definitions. I know, I'm sorry. The cardinal number of a set. This is the set W has a cardinality of 6. What this means is the number of elements in the set, and if you look at the W that we were using earlier, it has 1, 2, 3, 4, 5, 6 elements in it, so the cardinality is 6. We use the notation N in front of the name of the set written in parentheses. This is read N of W, or the number in W, or the cardinality of W. And it's going to give you just a specific number. Notice this is not a set, it is not in braces, it is just a count of how many things are in there. And when you have a set, you can theoretically have repeated elements. So I could have listed 1, 2, 2, 2, 3, 4, 4, 4, 7, 5, whatever, no 7 in there. But it would still be the same set. As long as, you can have repeated elements all you want to. And then if it does have repeated elements, you only count them once. It's like having extras in there, it's just not simplified yet. Okay? Okay, now, right here, equivalent sets. 2 sets are said to be equivalent if they contain the same number of elements. So if the number of elements in A is equal to the number of elements in B, then we say A is equivalent to B. Okay. One-to-one correspondence. Sets A and B can be placed in a one-to-one correspondence if each element in A can be paired up with exactly one element of B and vice versa. So if I had the sets 1, 2, 3, and that's my A, and then I had B equal to 4, 5, 6. They're not the same set because they have different elements, but their cardinality is the same because they both have 3 elements. And this is one-to-one because I can pair these up. I could pair the 1 with the 4, the 2 and the 5, and the 3 with the 6. And I don't have any extra over here that haven't been paired up. I don't have any extra over here that haven't been paired up. Everything makes a pair and you have nothing left over. It's a one-to-one correspondence. Okay? And by definition, if you can put these in a one-to-one correspondence, you have the same number of elements. It just doesn't work otherwise. So if you have a one-to-one correspondence, then the 2 sets are equivalent. So let's go on here. We're still talking about cardinality. Finite set and infinite set. A finite set means a set whose cardinality is a natural number or 0. So it ends. It might have nothing in it. It might have 2,503,000 elements in it, but it does stop. Okay? An infinite set is a set whose cardinality is not 0 or a natural number. So it would be a set that just continues on and on and on and on. So the set of all natural numbers would be an example of that because theoretically you can count forever. There's no end point to it. Okay, so now a big distinction that gets confusing. Right here, we had equivalent sets. Okay, here we're talking about equality of sets, and they are different, and we have to be really careful about keeping them separate in our heads. Okay, for equivalent, we're just talking about the number of elements in there. If they have the same number of elements, they are equivalent. But to be equal, the set it has to have exactly the same elements. And we would write set A is equal to set B. These two are not equal because they contain different sets, but they are equivalent because they contain the same number of elements. Okay? Now, if the two things are equal, then they definitely have the same number of elements. Okay? All right, so let's work some example problems. We're just asked if these are well-defined or not. Okay, so could a reasonable person decide whether or not something belonged to it? So if I had the collection of part-time and full-time students currently enrolled at your college, I don't know what that number is, but I could find out, there is a fact, I could go find out how many people are enrolled, and I could easily tell whether or not somebody was enrolled or not. So this one is well defined. I don't know off the top of my head, but the information is there. It could be determined. Let's try this one. The collection of the 5 worst prime ministers of the United Kingdom. Well, there are probably a couple who everyone could agree on, but this is an opinion, the worst. And we might be able to agree on some of them that are definitely among the worst, or we might be able to agree on some of them that are definitely not among the worst. But we're going to argue about those in the middle because it's an opinion. And if there's any room for argument, it is not well defined. Okay. Let's try this one. We want to rewrite these sets using the roster method. And the roster method was the one where we just list everything. So the set of months of the year that have exactly 30 days. Okay, so remembering the rhyme, 30 days have September, April, June, and November. Okay, and all the rest have 31 except for February, which has 28. And then you also have the method, the knuckle method, where you count. If you're on top of your knuckles, it's 31. If you're between your knuckles, it's either 30 or 28. So January has 31, February, March, April, May, June, July, and then start over again, August. So July and August have 31, September, October, November, December. Whatever it takes for you to remember that, use it. Okay. Now, the set of even natural numbers less than 10. So I'm going to need to put these in braces. Even natural numbers. Now, I would start with 1 for natural numbers. So my evens would be 2, and then 4, and 6, and 8. And I'm going to stop right here and double check here. This says strictly less than, so I'm not going to include 10. If this were less than or equal to, I would put a 10 right there. Okay. So let's try this one. This is written in set builder notation. This says, I want everything that is a natural number and is less than or equal to 4. So natural numbers begin with 1, and then 2, and then 3. And the next one would be 4. It's allowed to equal to, so this time a 4 is included. Okay. Now let's try this one. The set of all x such that x plus 3 equals 9. Now you may, what we actually need to do, you're likely doing this in your head. But simple algebra problem, if I subtract 3 from both sides, I get that my x must equal 6. So all of the x's that make this part true, the only one there is 6. So your answer is 6 written inside braces. This is the only element, this is the only number that you could plug in here and have it work. Okay, so let's try this. We want to rewrite these sets that are listed in roster method, and we want to write them in set builder notation, and there are multiple ways you can do this. Okay, so let's try here. I know that these always start off the set of all x such that. Now I just need to describe what these are. I'm starting at 36 and I start counting up by 1. These are all natural numbers, and the ellipse here says it continues on forever in the same pattern. Okay, so it looks like my x needs to be an element of the natural numbers, and we're imagining that that's in bold. Okay, and I'm starting at 36 and going up, so I could say x is greater than or equal to 36. So I start with my natural numbers, I start at 36, and I start counting. Okay, and that would build it up. An alternate way of doing this would be the set of all x such that x is an element of n, and x is strictly greater than 35. Here I would not include 35 because it's not equal to, so I would be starting at 36, which is what I'm asked to do here. Or I can put the equal to and do the 36. These are both legitimate options. Okay, let's try this one. It's very similar. We have roster method here. We have, again, natural numbers listed, but this time they don't go on forever. They stop at 59. So I'm going to do the set of all x such that x is an element of n, and my x values need to be between 36 and 59, and I'm just going to use the equal to's here. Just telling you your start point and your stop point. Again, this could be rewritten with less thans without the equal to, or even a combination of less than and less than or equal to. There, you have options here, but I just go with the one that I think is easiest, as you should too. Okay, so let's go on to these. We want to determine which of these make up the empty set. Okay, is this the empty set or is it not the empty set? This one says the set of all x, where x is a woman who served as US president before 2016. Okay, well, we haven't had a woman president yet, not an official one anyway. Look at Woodrow Wilson's wife. And before 2016, well, if there were a woman who had been US president before 2016, we could tell whether or not they belonged. So this is a well-defined set. It just doesn't have anything in it. So your answer here is just the empty set. Okay. The set of all x such that x is the number of living US presidents born before 1200. Well, the US didn't come into being until 1776, and I know we didn't have anybody born before 1200 who was still alive then, so the answer is going to be no solution. But even then, the number of currently living people, I don't think so. You can even ignore the US president bit here. This is no solution. This is the empty set. Sorry, we also use that for no solution. Okay, so let's try this one. The set of all x such that x is a natural number and is between 3 and 7. Well, there are numbers in there that would work. I could rewrite this as, let's see, 4, 5, and 6. Because these numbers are natural numbers and they are between 3 and 7. So this is not the empty set. Now some true and false questions. This is mainly, do you know your notation? Is 8 an element of this set? So I look at this and I look for a pattern. I have 1, 3, 5. It looks like I'm dealing with only odd numbers, starting at 1 and going to 19. 8 is an even number, so this would be false. If you were given 8 and then a blank and then that set, you would put this symbol between it, not an element of. Okay, so let's check here. This says 26 is not an element of this set. So let's look here for a pattern. These are all natural numbers. I'm counting up by 1. Am I going to hit 26 in there? Yes, because I stop at 50. So 26 is somewhere in here. This says it's not an element. It would be an element, so this is false. Okay, it's this one. 20 is not an element of the set where x is an element of n and x is less than 20. Well, 20 is an element of the natural numbers, but 20 is not less than 20. So this says it's not an element. It is not an element, so this is a true statement. Okay. Find the cardinal number of each set. Now remember, this is just asking how many elements are there in the set. So right here, I'm asked to find the number of A. And I simply count the number here since this is listed in roster method. 1, 2, 3, 4, 5, 6. So the cardinality of set A is 6. Now, let's say our set C is defined as a month of the year that begins with the letter W. So I'm looking for the number of C. And I go through the list of months in my head, and we don't have any that start with a W. So the cardinality of set C is 0. It has no elements in it. Another way of writing C would be the empty set. It has nothing in it. Okay. B is the set of all natural numbers where our x is between 3, or 3 is less than or equal to x is less than 10. And we want to know how many elements there are in here. Now you may want to just list out the numbers that are here. I'm using natural numbers. I start at 3 because it has an equal to, and then I have 4, 5, 6, 7, 8, and then 9. I'm not allowed to equal 10 because this doesn't have an equal to on it. So what is that? 7 elements. So the cardinality of set B is 7. Okay. Last bit here. We're supposed to determine whether these sets are equivalent and then determine whether they are equal. Remember, equivalent, they have the same number of elements. Equal, they have to be exactly the same. So for part A here, are these equivalent? I'll go ahead and label these. That's part A, and let's call this part B. Part A, are they equivalent? Do they have the same number of elements? This has 5, this has 5, so yes, they are equivalent. Now for B, are they equal? Do we have exactly the same elements? And these could be in different order. As long as they're the same ones, they would be equal, but we don't have that here. We have very different elements. So no, they're not equal. Okay. Same thing here. We have sets A and B, and we want to know if they are equivalent, and then if they are equal. The first thing is that we have a bunch of repeated elements here, and we know we don't want to count them all separately, so I'm just going to rewrite this. I have a 0, I have 1, I have a 2, and I have a 3. It doesn't matter how many times it's written. It just matters what elements are in there. So are these equivalent? Do they have the same number of elements? Well, they both have 4, So yes, these are equivalent. And then B, are they equal? Well, it's written in a different order, but that's okay. I have 0, 1, 2, and 3. These two sets are exactly the same. So yes, these are equal. Okay. Again, are these equivalent or equal? A is the set of students at your college, and B is the set of students majoring in business at your college. Now, I don't have those numbers, but I do know that not everyone at our college is majoring in business. So I know this number is going to be bigger than this number. Okay, so if I list all the students at the college, I'm going to have more numbers, I'm going to have more elements in there than I will here. So what I know is the number of A is somewhat bigger than the number in B. That's what I was just trying to say. Okay, so are these equivalent? No. Not everyone at our college is a business major, so they don't have the same number of elements. For B, first of all, if they're not equivalent, if they don't have the same number of elements, they definitely don't have exactly the same elements. So these are not equal either. Now I do want to point out the combinations here. You can have some that are equivalent and then not equal. You could have some that are both. And then you can have where they're both not. Okay? What you will not see is like part A being no and part B being yes. This is never, ever going to happen. Okay, our last bits here. We want to just decide whether these are finite or infinite sets. So could I theoretically list everything in there? Here, my x is a natural number, and my x is larger than or equal to 50. Well, I would start at 50, and I would keep counting up, right? 50, 51, 52, 53. Do I have an endpoint? No. This one is infinite. I mean, I know the rules to keep going. I could keep listing as many as I wanted to, but I could never finish listing them all. And here, my x is a natural number, and it is less than or equal to 1,273,489. Could I theoretically list everything that's in here? Well, yes. I'd start at 1, and I'd count all the way up to this number. It's a big number. It's going to take a long time, but I will eventually be able to stop. So this is a finite set. Okay, and that will be it for this section.